Hi everyone, I'm Sule. I'm a PhD student in the particle physics group. I will mention my project's a bit more obscure. I feel like we've had some really relevant talks, so please bear with me. So I wanted to talk about how we're employing sustainable computing in particle physics and how we're trying to reduce how much computational power we're using on our research. So I'll start with a brief overview of what we do and what the problem is, and then I'll kind of talk you through my project, which is how we simulate it, well, we simply improve the speed of simulations a lot. So when I say particle physics, our job is to kind of study what we are all made of. So you might have heard of atoms, molecules, protons, neutrons, or the recent, like 2012 Higgs boson, the God particle. And we want to study the properties of these particles and kind of how they behave and learn from it and to understand why we are the way we are. And the way we study this is by we bash them into each other, and if they have enough energy, they will produce more of the rare ones. And if you're lucky, it will produce, it will produce the Higgs boson. And what you really want is just to see one particle, but what often happens is that it's producing all of the extra ones. So out of this entire mesh of extra stuff that's produced, you only want to do one. So in our context, what we do is we do a bit of simulation work. So we kind of see what the data is like, and we use this thing called Monte Carlo integration. So long story short, you can calculate the probability or the chance of one of these extra particles to be created. You generate a random number, and if this random number is smaller than the chance, you generate the particle. You do that enough times, you can actually get a very close representation of what happens in our particle accelerator and things like CERN. And once you've done that, we use it to compare it to the data you see at these accelerators. Where there are deviances, that's where our current understanding of the universe is not quite right. Anyway, I guess that's kind of just more of the context. I'll kind of highlight now what the problem is. So to do all this research, we use a lot of electricity. And there's already how much electricity we use at the detector. We also have to study the data and kind of manipulate it before we can get actual physics results. So these whole institutions are funded by governments, and they give us a certain sustained budget. So in this graph you can see this is kind of the annual CPU consumption. So this weird unit is like kilowatt hours, but this is 1 million watts per year. And this is just the time as of now. So based on our budget, we need to be inside these two black lines, but given 2027 is that close, we're already going to skip it. And we'd have to really do some aggressive slowdown, or else we won't be able to fund a lot of our projects. So like I said earlier, all of this simulation stuff actually takes up 17%, which is like a massive chunk of all of this, the budget that we have. So we are all kind of working on trying to figure out how we can reduce our computational usage in this scenario. So short-term solutions like this involve kind of studying the code, studying where the simulations take the longest, and trying to improve that. And that's what we call finding bottlenecks in the profiler. But the long-term solution is to use advanced computational tools like devices like GPUs to simultaneously simulate these things. So it's a lot of this is being done for particle interactions, and for my PhD, I'm working on how this can be applied to generating new particles based on probabilities. So I'll just give you a very brief example. So you start with, I guess, one interaction where I've had two particles interact, it's formed the Higgs boson, nothing else. I say, what is my probability of a new particle to be generated? I generate a random number. If it's lower than this probability, you accept it and you new particle in your code. On the off chance, if the random number is higher, you have to start the whole process again at a lower energy. And this is the problem. We have to do this again and again until it's accepted. So what we would do on a computer would be do the first one and then do the second one and wait until the second one is accepted. So one thing that I would like you guys to notice is that, perfect. You can see that although the paths are longer, you can see that a lot of these lines, or a lot of these steps are the same. And for that we can make use of GPUs. So what GPUs do is they split repetitive tasks and execute each of the steps in parallel. So it's originally for video games, but they're using data center for fast analysis and machine learning. And the best way to kind of understand this is that if you have to write like a sentence, you would use a pen for it. But if you have to write the sentence again and again and again, you can just use a stamp, right? You just stamp it on and it'll speed things up. So yeah, GPUs are this. While your computers have these things called CPUs, which have these very powerful chips, and it will do one specific task. These GPUs have much less powerful chips, but they can do all of these tasks in parallel. So my only suggestion was, as we saw that all the steps were the same, why don't we just turn off some of the chips where the new particle is not accepted, and just make the particle for the other simulation systems. And yeah, that's all there is to it really. And we wanted to see how much it benefits, and it turns out it produces identical results as before. And this is on a scale of 1, 10, 100. It's actually 250 times, 257 times faster, which means it's equivalent to almost using these 275 cores of its CPU. So to kind of bring it all into context, we compared how like one Intel chip would compare to one NVIDIA GPU, and if we're again just assuming it's going to take somewhere around 275 CPUs, and if an Intel Core has 16 chips inside, it will actually be much cheaper to have one GPU and a small chip than having like 16 CPUs. And most importantly, when you look at the power consumption, you're reducing this by 5 times. And if you do it this way, yeah, you're saving a lot more electricity. And again, going back to our original graph, coming back into that sustainable budget border. But yeah, this is all available online for people who are really into programming or into sustainable computing. And yeah, it's all open source, and the papers published as well. That's about it. I hope for some just people.
Does anyone have any questions for Sid?
Yeah, regarding about the CPU and GPU and the last row about the power, it's 250 watt and then 185 watt. You said this one is more consuming energy?
So the GPU definitely consumes more energy than like an Intel CPU, but you need 16 of them to kind of keep up with the GPU, and that is 85 watts would be around 1360. So that's how you can save your computational usage. So we're trying to say that if you have a GPU, you can use that as an alternative to a computer cluster, which uses a lot more electricity to run.
Thank you.
Thank you, Sid.